Have you ever pondered about the existence of naked singularities and their implications? These theoretical astrophysical phenomena, if they exist, could challenge our understanding of space-time and the cosmos itself. Dive into this intriguing world of astrophysics as we explore the concept of naked singularities. Firstly, let's demystify the Kerr metric. Now, the Kerr metric is a solution to Einstein's field equations of general relativity. This metric describes the geometry of space-time in the vicinity of a rotating black hole. Unlike a non-rotating black hole, where the singularity at its center is a point, a rotating black hole, as described by the Kerr metric, has a ring-shaped singularity. Picturing this rotating black hole, think of an ice skater spinning on one spot. As they pull their arms in, they spin faster, right? Similarly, the faster a black hole spins, the smaller and more flattened the ring singularity becomes. Now, why is this important? Well, because perturbations or disturbances in the black hole's spin can potentially lead to changes in the geometry near the singularity. Consider a spinning top. When it's spinning perfectly, it's stable, but the moment it starts wobbling, that stability is compromised. In the same vein, changes in a black hole's spin could potentially destabilize the event horizon, which is the boundary beyond which nothing, not even light, can escape the black hole's gravitational pull. Now, when we talk about extreme spinning black holes, we're referring to black holes spinning close to their maximum possible rate. These black holes are particularly interesting as they pose intriguing questions about the stability of the event horizon. In addition to the event horizon, we also have the ergosphere. This is a region outside the event horizon where objects can't remain stationary. Within the ergosphere, the black hole's rotation drags space-time along with it in a phenomenon known as frame dragging. The dynamics within the ergosphere can affect the singularity and the event horizon, adding another layer of complexity to our understanding of these extreme cosmic entities. So, extreme spinning black holes pose intriguing questions about the stability of the event horizon and the ergosphere. As we delve deeper into the cosmos, we're continually unearthing new questions, and the Kerr metric provides us with a framework to explore these questions and further our understanding of the universe. Now let's delve into the Reissner-Nordström metric. Named after Hans Reissner and Gunnar Nordström, this solution to Einstein's field equations represents a charged, non-rotating black hole. Unlike the Kerr metric, which describes a spinning black hole, the Reissner-Nordström metric is static. Its defining characteristic, however, is the presence of an electric charge. The electric charge introduces a new parameter into the geometry of space-time around the black hole. This charge, along with the mass, determines the location and structure of the event horizon. The event horizon, as you may recall, is the point of no return. Cross this boundary and not even light can escape the black hole's gravitational pull. Now consider a black hole that's not just charged but overcharged, its charge exceeding its mass. The Reissner-Nordström metric predicts an intriguing possibility in this scenario. The excessive electric repulsion counteracts the gravitational pull, disrupting the event horizon and exposing the singularity at the heart of the black hole. This exposed singularity, not hidden behind an event horizon, is what we call a naked singularity. It's a concept that challenges our understanding of the universe, as it seems to violate the cosmic censorship hypothesis put forward by Roger Penrose. This hypothesis suggests that singularities, these points of infinite density where our understanding of physics breaks down, should always be hidden from the outside universe. However, it's important to note that these naked singularities are purely theoretical. In the real world, the process of overcharging a black hole to the point of disrupting the event horizon is far from straightforward. It's not yet clear if such a scenario could occur naturally or if it's even possible at all. So, what's the bottom line? The Reissner-Nordström metric presents a fascinating study of charged black holes and the potential for naked singularities. It's a reminder that the universe still holds many mysteries waiting to be unraveled. Overcharging a black hole can theoretically disrupt the event horizon, leading to a naked singularity. Scene script. Let's turn our attention to Hawking's area theorem. Hawking's area theorem is a fascinating and fundamental concept that arises from the theories of general relativity. It's a theorem that revolves around the idea of an event horizon, which is the boundary around a black hole beyond which light cannot escape. And according to Hawking's area theorem, the surface area of this event horizon can never decrease. You see, when a black hole forms from a collapsing star, it creates a region of space where the gravitational pull is so intense that nothing, not even light, can escape from it. The boundary of this region, the event horizon, is effectively the point of no return. Now, Hawking's area theorem states that the total area of the event horizons of any collection of classical black holes can only increase over time. It can stay the same or it can get larger, but it can never get smaller. This is due to the irreversible nature of gravitational collapse. This theorem has profound implications for our understanding of black holes. For one, it implies that black holes can only grow in size. They can't shrink. If you throw something into a black hole, the event horizon will grow to incorporate this new mass. The theorem also tells us that if two black holes merge, the total area of the new event horizon will be greater than or equal to the sum of the areas of the original event horizons. The inescapable conclusion from Hawking's area theorem is that increasing a black hole's mass enlarges the event horizon. This is straightforward enough. But what about decreasing the mass? Could this violate the theorem? On the surface, it might seem so. But remember, the theorem states that the area of the event horizon cannot decrease. It doesn't say anything about the mass of the black hole itself. So while it's theoretically possible for a black hole to lose mass, it's unclear how this would happen without violating the fundamental principles of the area theorem. And that's where the mystery lies. It's unclear how mass loss near the singularity would impact the stability of the event horizon. Opening, what would it take to expose a singularity? Let's dive deep into the cosmic censorship hypothesis, the guardian of our universe's decency, proposed by the brilliant Roger Penrose. This hypothesis posits that singularities, these strange entities of infinite density, are always hidden from our view, tucked away behind the event horizon of a black hole. But what if we could disrupt this event horizon? It would require extreme conditions, potentially violating the no-hair theorem, which suggests that all black holes can be completely described by just three parameters: mass, charge, and angular momentum. Now let's get quantum. Quantum gravity effects near the singularity could play a key role in exposing these elusive entities. Think of models like loop quantum gravity, which propose a discrete structure of space-time at the smallest scale, the Planck scale. We're talking about the fabric of the universe itself, woven with threads of the tiniest possible units. But understanding how quantum behavior works in such extreme proximity to a singularity is like trying to read a book while standing on a speeding bullet train. Finally, let's talk about energy conditions. The Hawking-Penrose singularity theorems rely heavily on certain energy conditions. These are like the rules of the game for how energy can be distributed in the universe. But what if we deviate from these conditions? What if we introduce exotic matter or unusual energy distributions? This could influence the fate of the singularity and potentially strip it of its cosmic camouflage. The quest to expose a singularity is a journey through the very extremes of the universe, where the rules of physics as we know them might not apply. It's a journey through space-time itself, to the very heart of a black hole, where everything we think we know about the universe could be turned on its head. Closing. Understanding quantum behavior close to the singularity is a complex challenge. Let's now explore the challenges and speculations surrounding naked singularities. Diving into the realm of quantum gravity, we find ourselves on the frontier where general relativity and quantum mechanics collide. It is here, near the singularity, where quantum effects become dominant, challenging our classical understanding of the universe. Then we come face to face with the information paradox. This conundrum revolves around the fate of information that plunges into a black hole. Resolving this paradox is crucial for understanding the quantum nature of black holes and might shed light on the possibility of naked singularities. Imagine considering space-time as a dynamic entity, an entity that might be evolving near the singularity. This perspective adds layers of complexity to the problem, making it even more intriguing. Speculations and theories extend our thinking in provocative directions. For instance, understanding particles near the innermost stable circular orbit is critical for the accretion process and affects the structure and stability of the singularity. Moreover, the chaos and mixed-master universe theory, extensions to general relativity like scalar tensor or higher dimensions, and speculations on topology changes near singularities could all alter the spacetime structure and the visibility of the singularity. Finally, incorporating quantum cosmology and the Wheeler-DeWitt equation addresses the quantum nature of singularities, pushing the limits of our understanding. These challenges and speculations continue to fuel the ongoing research and drive the quest for knowledge in the field of astrophysics.